Okay, so what we're doing, we're looking at heat source systems. And what we are going to do, we are going to work an example problem involving heat source systems. So I'll begin by writing out the example problem. And what we'll be doing is this will be an application involving rectangular coordinates. We'll be looking at a plane wall or a slab. So let me write out the problem statement. Okay, so there's our problem statement. What we have is a plane wall, and we're told that it has uniform heat generation, and the heat generation rate in watts per meter cubed is Q dot. We're told that it is insulated on one side, so that is a piece of information, and then the other side is exposed to a convective environment, and the conditions of that convective environment are T infinity and H. And then what we are asked to do, we're asked to solve for an analytic expression describing the wall's temperature profile. So that's a bit of a hint there that we're going to be using the heat diffusion equation in this problem. And the last thing it says is knowing the wall's thermal conductivity K. So that will be one of the parameters that we're going to use when we are performing the solution for this. So what we'll do, we'll begin by writing out what we know. We'll come up with a schematic, and then we'll work through this problem. Okay, so that has what we know. We know the internal generation rate, we know the convective condition, we know the thermal conductivity. We're looking for the temperature distribution as a function of position. We will assume this to be a steady state problem, 1D, and the thermal conductivity is a constant. We will also assume the width of the wall, and so the width of the wall that we will assume will be width L. And so what I'm going to do now, I'm going to write out a schematic. Okay, so there is a schematic of our wall. One thing I forgot to add here was our convective environment. Okay, so there we have our conditions. Now, the boundaries on the walls, what we are going to do, let's check the problem statement. It said nothing about the temperature on the right-hand surface, but what I'm going to do, another assumption I'm going to make, is I'm going to say that the temperature at that point is T1. Another thing that we can say, if you recall the boundary conditions that we had for the heat diffusion equation, whenever you had an insulated surface, that meant that there was zero heat flux at that point. So with that, we can make a comment here. We don't know anything about the temperature at the left-hand surface, but we do know something about the change in temperature with position, the slope of it from Fourier's law. And we know that Q is 0. If Q is 0, dt by dx is 0. And consequently, we can write out for the other boundary condition, dt by dx, and I'm going to say this is x equals 0. I didn't put the coordinate system, but I will. That is equal to 0. So the coordinate system in this problem, we will assume that our wall begins here and then moves in that direction. And consequently, this would be x equals L. This is x equals 0. So that is the schematic for this problem. In terms of analyzing this, we want to come up with an analytical solution, and consequently we'll be using the heat diffusion equation in order to do that. So let's begin the analysis. Okay, so that is the heat diffusion equation. Looking at this, we can reduce the complexity of it right off the bat. So first of all, partial with respect to y. Well, we said that this is a 1D problem, so consequently partial with respect to y and partial with respect to z, those two are going to go to 0 and they're going to disappear. And then on the right-hand side of the equation, we said that this was steady state. And consequently, the temperature would not be changing as a function of time. So that term disappears as well. And with that, we quickly are able to reduce the equation into something that looks a little more friendly. And I'm going to bring the heat generation term over to the right-hand side of the equation. Now, looking at this, we can do a further simplification, and that is to looking at this, the fact that it's only a function of x, we can change that partial differential into an ordinary differential. So we can write so given it's 1D, we can assume that t, oops, I apologize, that should not be an x and a y, that should be a y and a z. So t is not a function of y and z, and consequently, the partial with respect to x can be expressed as an ordinary derivative with respect to x. And with that, the mathematical physics equation governing this problem, the heat diffusion equation, reduces to the following. Okay, so that's something that looks a little bit easier for doing analysis. And so how do we solve for the temperature profile if we have an ordinary differential equation? We're looking for this. The way that we solve for that, we integrate, and we integrate twice because it's a second derivative. So we will integrate this twice. And so on the first integration, we get a constant of integration. We don't know what that is yet. The way that we're going to solve for that, we'll apply boundary conditions. We integrate it a second time. And we get a second constant of integration. So in solving for C1 and C2, we will apply the boundary conditions. And if you recall back, let's look at our schematic, which was back here. Where the heck was it? There it was. Okay, so one boundary condition is what's going on the left-hand surface over there. Another boundary condition was at that location. And then there actually is another one, and it relates to the heat generation, basically doing an energy surface balance right here. And so we could do another one there. But let's take a look at the boundary conditions now. So those are three boundary conditions that we have for this problem. We only have two constants of integration, and consequently we only need to use two of these. What we're going to do in the solution here, we're going to use the first two. And so let's apply those and use them to determine. And you'll notice the third one here, this is the one that I said was related to an energy balance on the right-hand surface. And that's Q dot times the volume, and that has to be equal to the energy that is flowing out and going into convective heat transfer. So that's the relationship that we've made with that third boundary condition. So let's go ahead and proceed to use the first two boundary conditions. So what we find by applying the first boundary condition, which is the one of the insulated wall on the left-hand side of our slab, when we apply the first one, we get C1 is equal to 0. And then applying the second boundary condition, and so this is what the second boundary condition reduces to. It's not as clean as the first one, but what we're going to do, we're going to take this, and we're going to plug it back into our equation here. So let's plug those back in and see what we obtain. So this is what the temperature profile in the wall turns out to be with internal generation. So recall we had a wall like this, we had insulation over here we had a free convective environment. And what this is telling us is it's telling us temperature as a function of x, and x is going starting at this location here. So it gives us the temperature distribution. So what we will do, and it assumes that we know the temperature on that wall, and we know Q dot, we know K, and the width of the wall, L. So what we're going to do in the next segment, we're going to plug in some values, and we're going to see what this temperature distribution looks like.